Chapter 4, Part 7, Conformations of Cyclohexanes. So cyclohexane is incredibly common in nature because the six-membered ring is perfect in a lot of ways. And so this actually gets its own video because there's so much to talk about. So for one, cyclohexane, even though we draw it as a hexagon, is not really in a perfect hexagon in real life. Its more stable form is this, what we call chair form, where you could picture these four atoms more or less in the same plane, and this one would be below the plane, this one would be above that plane. So if you were to look at it from the side and see an overall Newman projection, looking down those bonds that I showed you a second ago, like this, you would see that every single piece of that is perfectly staggered. And this is true no matter which bond angle you look down. So this is one thing that's really great about cyclohexane, is that it happens to have perfectly staggered 109.5 degree bond angles on every single atom. Now there are also less stable conformations of cyclohexane, such as this boat form, which also has 2 and 3 and 6 and 5 in plane with each other, but bringing carbon atom 4 down causes a weird kind of problem. So notice that every single thing is eclipsed in this format. This is obviously not good. This is a very, very high energy, unstable conformation. So there are a lot of reasons that the boat conformer is not great. So first of all, everything is eclipsed. There's also something called 1,4 flagpole interactions, which we'll illustrate in a second. So all of these bonds, first of all, are eclipsed. And then everything that is on carbons 1 and 4, let's say that they're hydrogen atoms, is going to be trying to share the same space right here. And when it's hydrogens, it's not too bad, but imagine if those were methyl substituents trying to take the same space. So those are called 1,4 flagpole interactions, and they are incredibly unfavorable. There's also one more really low energy conformer that is more of a halfway point between going between chair and boat, but it's even lower energy than the boat conformation. So we have the chair conformation, which is way at the bottom, very low energy, very, very stable. You can go up to half chair, which is on the way to the boat, where you've brought up one of the carbon atoms to be in plane with the other 5. And that's really high energy. It does not stay there very long. It can go down to twist boat, which is a little better than boat. And then boat is going to be your most common of the high energy, low stability conformers. Back down to twist boat, back up to half chair, and down to chair. So this brings us to substituted cyclohexanes. Since the six-membered ring is the most common ring found in all of nature's organic molecules, you can imagine that it appears frequently, but not as plain cyclohexane. It's going to have stuff on it, and that stuff on it is going to impact the preferred conformer and also the stability of the molecule. So the chair conformation of a cyclohexane ring has 2 distinct orientations for the bonds that project from the ring. They are called axial and equatorial. So I've color-coded it here, where everything that is in the axial position is in blue, and everything that is in the equatorial position is in red. And this is kind of hard to see on paper, and I did make a separate video of this that you can watch on my channel, but everything that is axial is running up and down through the molecule. So that's all of these bonds where the hydrogen is blue. And if you were to look at an actual model of cyclohexane, you can place that model in your hand and all 3 of these atoms will touch your hand. and you'll see that all of those blue hydrogens are sticking straight up and down. And then if you were to look down from the top of the model, you would see the red hydrogens creating a ring around the molecule. They're sticking off to the side. This is why they are called equatorials, because they kind of create like an equator around the molecule. When I do this in class, I switch to the document camera. That's what this is saying. When you draw the chair conformational structures, it's really important that you draw it correctly, because you're going to have to illustrate your equatorial and axial positions. So I'm going to do a little bit of a tutorial with showing you how to actually do that, how to draw a good chair conformation. So it's all about drawing multiple parallel lines. So draw one parallel line, draw the other. And then I usually go from this direction. So now I have two parallel lines. And then I close it up like so. So notice that the lines that are the same colors are parallel to each other. And that's what makes a good chair structure. Now the reason this is important is that if you don't draw it well, it's going to be really hard to illustrate your axial and equatorial positions. So the tricky thing is actually placing the axial and equatorial positions. So looking at this carbon, the carbon is pointing up, and so the axial position is going to point up. The next carbon over is pointing down. It's creating like a downward V. So that axial position points down also. Now notice that this V kind of points up. So that's the direction that the axial position goes in. Now it alternates up, down, or going around the ring. And so once you have one placed, you can put all the others on there. Now the next set is the equatorial. And those always point in the opposite direction. So if the axial is up, the equatorial needs to be pointing more down. And it's not going to be a directly up and down line. It's going to be off to the side, angled downwards. So the next one over, the carbon was pointing down, the axial position is pointing down, so the equatorial position points up. The next equatorial position must point down, up, down. Now also the, oops, I missed one. The equatorial positions that are across the molecule from each other should be roughly parallel. So these two are parallel to each other. These two are parallel. And then the ones in the middle are parallel to each other. And this does take practice, so just draw it over and over. And then you can also draw the chair leaning in the opposite direction, and we'll talk about why in a little bit. But you just follow the same process. And then all of your positions, same process. Oops. Brain part. Okay, there we go. Oh, I guess I had it illustrated. So now let's talk about the axial and equatorial positions in more detail. So the axial hydrogens point up and down. The equatorial hydrogens point off to the side. Okay, so let's talk about what happens when you take one of those hydrogens and you substitute it for something larger, such as methyl cyclohexane. Now, because these bonds have kind of free rotation around them, although they are a little more locked in because of being in a ring, it can do something that's called a chair flip, which is much easier to demonstrate in a model, and so that's why I have a separate video that you can watch. But this methyl group can either be in the equatorial position or in the axial position. And it turns out that equatorial is a much more stable position because the equatorial positions are all much more spread out than the axial positions are, and so the methyl group is going to be further away from any other cluster of electron density. So, for example, notice in this illustration that all of the hydrogens have these 1,3 diaxial interactions. And that sounds really complicated, but it literally just means that on a carbon that is 3 away, you have something that is in the axial position, they're going to interact. So 1,3 diaxial. Now, if it's all hydrogens, it's not a huge deal. But when the methyl is in the axial position, it's now going to have interactions with the other axial hydrogens. And that's a big deal. That's a big problem because the electron density on this methyl group is going to be trying to share the same space as the electron density of those hydrogens. So the larger the substitution, the more severe those interactions become, and the less likely it is to spend any time in the axial position. So, for example, let's look at substituents of different sizes. The fluorine substitution is quite small, and so it spends almost equal amounts of time in the equatorial and axial positions because there's not a huge cost for fluorine to be in the axial position. Its interactions with the other hydrogen atoms that are axial are going to be minimal. But you size it up to something like methyl, and now the molecule is going to spend 95% of its time in the equatorial position, and the methyl group will only be in the axial position about 5% of the time. And the larger the group gets, so isopropyl and then T-butyl, the less and less time it spends in the axial position. So T-butyl, almost 100% of the time, is going to be in the equatorial position. So this brings us to our next concept, which is Cis-Trans isomerism in cycloalkanes. Cis and trans isomers reference the location of multiple substituents relative to each other. So for example, if something is cis, cis means same. So the two methyl groups are on the same face of the molecule. They can either both be pointing up or both be pointing down, but they would be on the same side of the carbon framework. If it's trans, trans means across. So one is on the bottom face of the cyclopropane and one is on the top face. They are on opposite faces. You can see this in any cycloalkane. So cis 1,2-dichlorocyclobutane versus trans 1,2-dichlorocyclobutane. So there's a common misunderstanding with cis and trans. Cis means both up or both down. Trans means that one is pointing up and one is pointing down. The common misconception is that cis means that both have to be axial or both have to be equatorial, and that's just not true, and it can be very misleading to think that way. So do not fall for that trap. So let's take a look at some disubstituted cyclohexanes. First, we're going to look at trans 1,4-dimethyl cyclohexane. So the methyl groups can either be diaxial, where both are in the axial position, because on the 1, 2, 3, 4 carbons away from each other, the up position is axial over here, and over here it's going to be down. They're opposite of each other. And if you do a ring flip, you're going to see that you can also put them in the equatorial position. And again, if you're not sure what ring flip means, watch the video. It's very helpful. Otherwise, this is very confusing. Once you do the ring flip, the methyl groups can be in the equatorial position, and they're both going to be equatorial because they are across the ring from each other. And that has one down, one up. This is trans. Now, if we look at the cis 1,4-dimethyl cyclohexane, in order for them to be cis to each other, they both have to be pointing up. Now, if on this carbon I can put this methyl group pointing up and in the axial position, across the ring on the fourth carbon, the up position that I need happens to be axial. And when I do a chair flip, I have the same situation. This methyl will become axial, this methyl will become equatorial. And so notice that they have the same substitution, 1,4-dimethyl, 1,4-dimethyl, but in the trans disubstitution, they can either both be axial or both be equatorial. For cis 1,4, they are going to be one axial, one equatorial, even though they're pointing on the same face of the molecule. So let's look at a different one. 1-tert-butyl 3-methyl cyclohexane. So our previous example was 1,4 substituted. This one is 1,3. So ideally, the tert-butyl group would be in the equatorial position. And since this is a trans molecule, I'm going to count 1, 2, 3 carbons away. I need to put a methyl group on this carbon pointing in the opposite direction of my T-butyl group. And since my T-butyl group is pointing up, this puts it in the down axial position. And if I do a ring flip, the tert-butyl group ends up axial and the methyl ends up equatorial. So the first structure is going to be much more stable because the giant tert-butyl group cannot possibly survive in the axial position. It's not going to stay there. So it's going to spend more time in this conformation than in this conformation. For the next one, if it's cis, then the tert-butyl group, when it's equatorial, oh, this is 1,4. Oh, yeah, okay, 4. Woo, panicked for a second. Cis 1-tert-butyl 4-methyl cyclohexane. When it's cis, it's going to have the same problem where if the tert-butyl group is equatorial and we have cis 1,4 substitution, the methyl group is forced to be axial. Okay, let's look at 1,2-dimethyl cyclohexane. We have cis and trans. So when it's trans, you can have them both in the equatorial position because the neighboring carbons are going to have opposite facing equatorial positions, or you can have them both axial. The better version is going to be if they are both equatorial. When it's cis, the carbons that are next to each other, the up position on one can be equatorial, but in the next carbon over, the up position is axial. So the methyl groups will both have to be, or one gets to be equatorial and one has to be axial. And in the chair flip, you have the same exact situation. So these are going to be in equilibrium. Neither one of these is better than the other. Whereas in our previous example, the molecule is going to live mostly in this conformation and rarely in the other conformation. Okay, last topic on this is bicyclic and polycyclic alkanes. So a good example of this is decalin, which is bicyclo-4,4,0-decane. And you can have cis and trans decalin. And the cis and trans here is actually that the rings are essentially substitutions on each other. So notice here that both hydrogens are pointing up. Here the hydrogens are pointing opposite each other.